An aircraft may touch down at nearly 150 knots, but at that exact moment, its landing gear wheels are still completely stationary. So the instant they hit the runway, they must accelerate from 0 to thousands of rotations per minute in a fraction of a second. If the brakes are applied too early, the wheels can lock, and the tires can be destroyed almost instantly. To slow any aircraft down safely after landing, 4 main braking systems work together. During flight, the landing gear stays retracted inside the wings or fuselage to reduce drag. Then during the landing phase, the fairing doors open and the landing gear begins to extend. To prepare for touchdown, the hydraulic actuator extends the landing gear. Because of the immense forces involved, side bracing provides crucial support. However, for maximum stability, a mechanical locking stay ensures the gear remains fixed and won't collapse upon impact. The nose landing gear also extends in a similar way, but its design is slightly different. It uses a rack and pinion system, which allows the aircraft to steer while moving on the runway. When the wheels touch the runway, they accelerate almost instantly from 0 rotation to a very high rotational speed. At the same time, the landing gear must support several tons of aircraft weight. This is why it works like a suspension system between the aircraft structure and the wheels, helping absorb the heavy impact of touchdown. The landing gear uses an oleo-pneumatic shock strut. In this system, the upper cylinder is connected to the aircraft structure, while the piston inside is connected to the wheel assembly. The piston contains an orifice, and a metering pin is fitted inside it. The shape of this pin gradually becomes wider toward the lower end. Pressurized nitrogen gas is filled in the upper part of the cylinder. During the landing impact, the piston moves upward, and oil passes through the orifice into the cylinder, compressing the nitrogen. But as the piston moves upward, the metering pin gradually reduces the size of the orifice. This controls the oil flow and keeps the nitrogen compression within a safe limit. After the shock strut absorbs the sudden impact, the compressed nitrogen pushes back. This pressure acts on the oil, causing the piston to move outward again. A shimmy damper is also fitted here. It controls the high vibrations and side forces that can occur during landing, helping the landing gear remain stable. Once the aircraft is on the runway, the next priority is to slow it down quickly and safely using controlled braking. Air drag helps slow the aircraft at first, but it is not enough to stop it within the available runway length. That is why spoilers are deployed. They increase drag and help make the wheel brakes more effective. Spoilers are mounted on the wings. During landing, they reduce lift and push the aircraft down onto the runway. This increases the load on the main landing gear and helps the wheel brakes work more effectively. When the pilot presses the brake pedals, the braking input is sent through control cables and valves to the wheels of the main landing gear. Most of the aircraft's weight is carried by the main gear, so the wheel brakes are most effective there. Normally, the nose gear does not have a braking system. A single landing gear assembly can have multiple wheel pairs, and disc brakes are fitted inside each wheel. Their basic working principle is similar to car brakes, but aircraft braking generates an enormous amount of heat. That is why aircraft brakes use multiple carbon discs. Drive keys are fitted inside the wheel, and the carbon discs are mounted on these keys. These discs rotate with the wheel, which is why they are called rotor carbon discs. The stator discs remain stationary and are fixed to the axle. An end plate is installed on one side and a pressure plate is installed on the other side. When the wheel assembly is installed, the rotor carbon discs sit between the stator carbon discs. A piston housing is fitted above the pressure plate, and it contains multiple pistons. When the brakes are applied, these pistons push the pressure plate and the stator discs toward the end plate. This compresses the rotor discs and applies braking force to the wheel. When the brakes are applied, friction is created between the tires and the runway, helping slow the aircraft down. But if the braking force is too high, or if the runway does not provide enough friction, the tire can skid or even burst. Let's understand this with a simple example. Suppose a wheel normally moves 1 meter in one complete rotation, but if the braking force becomes too high, the wheel may slip and move only 0.9 meters instead of the full 1 meter. That missing 0.1 meter is the slip. As the braking force increases further, the amount of slip also increases. A similar situation can also happen when the tires cannot generate enough friction on the runway. In that condition, even a small amount of braking force can cause a tire to skid, which can make the aircraft unstable. To prevent this problem, aircraft use an anti-skid system. The pilot cannot monitor the exact skid condition of every wheel in real time, because the main focus is to stop the aircraft safely and quickly. One of the main components of the anti-skid system is the wheel speed sensor, which is fitted on the wheel axle. The wheel hub is connected to the rotor of the speed sensor, so the sensor rotor spins at the same speed as the wheel. Near the rotor, there is a stator that contains a permanent magnet and a coil. As the rotor spins, the gaps in the rotor change the magnetic flux. When a gap comes in front of the stator, the flux decreases and reluctance increases. When the gap moves away, the flux increases and reluctance decreases. This changing magnetic flux creates a frequency signal. The faster the wheel rotates, the higher the frequency becomes. This means the signal frequency directly represents the wheel speed. These sensors are fitted on all braking wheels, and their data is sent to the brake control unit. This unit also receives the aircraft's reference speed. For example, if the aircraft is moving at 150 knots, but one wheel is rotating at a speed equal to 140 knots, it means that wheel is skidding, and the braking force is too high. In this condition, the anti-skid system automatically reduces the braking force on that wheel. Once the wheel speed comes close to the aircraft's reference speed again, braking pressure is restored. In an aircraft, each wheel brake is controlled separately. This is necessary because if one wheel skids more than the others, the aircraft can pull toward one side. To prevent this, anti-lock protection is used. If the speed of any wheel drops to around 30% below the highest speed wheel, the system releases the brake pressure on that wheel. Once the wheel speed returns to normal, braking pressure is applied again. A similar system is also used in cars. Tell us in the comments what it is called. A dangerous situation can occur if the brakes are applied before touchdown. The wheels can lock, and the moment they touch the runway, the intense friction can damage or even burst the tires. That is why, along with anti-skid protection, aircraft also use touchdown protection. For example, this landing gear has 3 wheel pairs: front, middle, and aft wheel pairs. During touchdown, the aircraft is slightly angled, so the aft wheels touch the runway first. Touchdown protection compares the aircraft's speed with the wheel speed. If the aircraft is moving at 150 knots and the wheel speed is 0, then when the difference is more than 50 knots, the system releases brake pressure from that wheel. When the aft wheels begin to approach their reference speed, the system also releases touchdown protection for the remaining wheel pairs, so braking control can begin on them as well. As soon as the aft wheels come close to the reference speed, the braking system becomes active on those wheels. This braking system is highly complex because the speed of each wheel is checked separately, compared with the reference speed, and then braking pressure is controlled individually. Brake pressure control is complex, and because failure must always be considered, aircraft use not just one, but multiple hydraulic brake systems. The normal hydraulic brake system operates first. If it fails, backup hydraulic systems, such as the center and left systems, provide braking support. These hydraulic systems have their own pressure sources. The pressure passes through metering valves, normal valves, and anti-skid valves before finally reaching the wheels. Now comes the fourth braking system, known as thrust reversal. In normal flight, the engine pushes air toward the rear, creating thrust that moves the aircraft forward. But after landing, that airflow can be redirected to help slow the aircraft down. Here, the engine itself does not reverse. Only the airflow is redirected. A thrust reverser assembly is fitted at the rear section of the engine, and it includes translating sleeves. After landing, when the outer sleeve moves backward, the airflow that normally exits toward the rear is blocked and redirected sideways and forward. This creates reverse thrust, which helps slow the aircraft down more quickly. Your support means a lot to us. We create original engineering animations with a small team, and you can support our work by subscribing to the channel. For more detailed engineering videos like this, make sure to subscribe. Thank you.